Hello, I'm Schwa, and if you let me, I'd love to be your math teacher. So today we have quite the special one for you guys, because we're going to be talking about multiplication in n. So when I say n, I sort of mean the natural numbers. So those are numbers ranging from 0, 1, 2, 3 onwards. So that's all the non-negative integers, or all the positive integers including 0, or positive integers and 0. Because 0, of course, is not a positive integer, unfortunately. It's neither negative nor positive. Okay, so we're also going to be sort of learning about induction proofs, maybe, because the way that you should maybe think about multiplication and maybe the natural numbers in general is very inductive, right? So there's some good ways to reason inductively, and then there's maybe also some not so great ways to reason inductively, which I might go into a little bit later. I have a personal vendetta against those exercises where it asks you to prove using induction some formula that you otherwise don't know how to derive. But anyway, here today, I think induction actually lays the groundwork for understanding, right? So I'm always an advocate for understanding, and in this case, right, if you've studied math at a more advanced level, or maybe you've taken advanced classes in high school, then maybe you've come across induction proofs, and your impression of induction proofs might be that they're difficult or annoying or difficult to understand, which, honestly, in a lot of cases, I'm honestly kind of inclined to agree. But today, this inductive way of thinking is actually gonna help us get forward a lot. So we really could not do any of this without this sort of inductive reasoning idea. So it's going to be important, right? And within an induction proof, there's I guess this is not an inductive proof necessarily, but we have a base case, and after that, we have some sort of induction step or induction assumption. I guess it's called an induction step, I think. But when we're defining this sort of, when we're defining this multiplication, for example, we're going to have basically an inductive rule, right? Maybe you could call it, well, it's not really a recursive rule. Maybe it's a little similar. But anyway, I mean, that's just terminology, right? Let's not get caught up in the terminology. We're basically going to have a base case, and then some way to some way to keep moving forward from that base case, right? So I don't know if I should maybe give an example of that. So if we know that the number 1 is a natural number, right, then we always know that the successive number to 1, that's also always a natural number. So for example, 1 plus 1, which is 2, that's a natural number. And since 2 is a natural number, its successor is also a natural number, so 3 is also a natural number. And because 3 is a natural number, 4 is also a natural number, and so on. So the fact that, assuming that 3 is a natural number, the next number is also a natural number, that's the inductive hypothesis. And then in order to make any sort of actual conclusions from that observation, we need to find some natural number. So for example, because 1 is a natural number, we also find that its successor is a natural number, 2 is a natural number, and then 3 is a natural number, 4 is a natural number because 3 was, and so on. So that's basically induction, induction in a nutshell. But yes, we're interested in the multiplication operation in the natural numbers. Now, I wrote this last, but maybe I shouldn't have written distributivity last, because distributivity is actually the inductive rule that we're going to use. So I would say that distributivity, it's not so much, and of course it depends on the way you define things and think about things, but to me, distributivity is not so much a property of multiplication, rather it's a defining property of multiplication, right? So it's not just something that happens to be true. It's something that we want to be true for the thing that we're constructing, right? So some of you might be confused as to what distributivity even is, so let me give you an example, right? So if we have 3 times 2 plus 4, then instead of computing it like this, we can modify this 3 separately and this 4 separately and then take the sum. So instead of taking 8, I can't do basic arithmetic. Instead of taking 3 amount of 6, let's first take 3 amount of 2 and then add 3 amount of 4 to it, right? Because 6 is made up of 2 and 4, so let's just modify 2 and 4 separately, and this will obviously give us 6 plus 12, which is going to be 18, which is the same as what we would have gotten if we computed 6 times 3. That's also 18, right? So no matter which way you do it, you get the same result. So that's distributivity. Distributivity basically says that this 3 that modifies this expression in a way because it multiplies it by 3, we can distribute that to the 2 and the 4, separately, right? That's what distributivity means. And I would argue that this is a defining property of multiplication. So multiplication is something that you can do in parts where we've also defined what it means to do for a very small part, So that's going to be the base case. Okay, we'll get to that later. But yes, that's distributivity, right? And it's a defining property of multiplication, in my view. Now, commutativity and associativity, on the other hand, those are not so much defining properties. Maybe commutativity. That could be a bit of a defining property. Let me actually think about this. Maybe. I think commutativity, there's a bit of, we kind of force stuff to be commutative in a way. What am I talking about? Sorry. No, commutativity, in my view, is a consequence of the definition, right? So while distributivity is like, okay, we want our operation to behave in this kind of way, I would say that commutativity is more of a funny little coincidence that it also happens to be commutative. And if you don't know what commutative means, I think we went over this in the last video, but basically 3 times 5 is the same as 5 times 3. You can swap the operands around. That's commutativity. Now, that's a funny, quirky coincidence, right? And I think I would say it's almost a surprising coincidence, because in the I think it was the previous video, I gave the example of distance between 2 points, which is a commutative operation. So that is not so, I mean, it's also like a property that you should prove, yes, but it's maybe not so surprising because you would expect that you just plug in two things and it doesn't matter the order that you plug the two things in. But if we interpret multiplication as, you know, and this is a completely reasonable way to interpret this. So we could interpret 3 times 5 as 5 plus 5 plus 5, while we could interpret 5 times 3 as 3 plus 3 plus 3 plus 3 plus 3, 5 times. So these are strictly different interpretations, right? So, you know, this 5 here carries on a different role than this 3, right? Because this 5 is telling how many numbers are we adding together, and this 3 is saying what is the number that we're adding to itself, right? So you wouldn't, like, right off the bat, you wouldn't necessarily, based on this, you wouldn't expect that this would obviously be commutative, but it still turns out to be commutative, which I think is a wonderful miracle of our mathematical world, that multiplication is commutative like this. Of course, when we define distributivity in full, you know, maybe you could sort of guess, but no, I don't know. I think this is quite wonderful. Yes. And another property that multiplication in N possesses is associativity, and that's another property that we went over in the previous video. So where should I draw this? So if we have 2 in the middle, then whether you multiply that by 3 first on the right and then 4 on the left, well, that's going to be the same thing as multiplying the 2 from the 4, sorry, what am I saying? The 2 by 4 from the left, and then by 3 from the right. So these two are the same thing. So that's associativity, right? And that's also, in my opinion, that is a pretty non-trivial thing, right? So if, like, I encourage you to try to reason through this, like, why would taking 2 amount of 3 and then taking 4 amount of that be the same thing as taking 4 of 2 and then that being the amount of 3 that you take? Like, why are those the same thing? To me, that's not obvious. To me, this is quite miraculous, but it turns out to hold. And the reason that it turns out to hold is because of this inductive principle. So, you know, we're going to basically think about, like, whether it holds in small steps, and we notice that, oh, it actually works in small steps, so therefore it's going to always work, right? So that's basically the idea. So that's what we're going to be doing, but first and foremost, let's actually define what multiplication in N is going to mean, right? That's going to be first and foremost. So let me take some more space for myself. Oh no, the camera isn't following me. That is a mistake by the director. I will have to give the director some harsh words after this recording. Let me see. How do you do this? So behavior. No, it was anchor. No, that's not right. I wouldn't say local. Yes, that's right. Okay, now I just gotta reposition the camera. You know, if I have enough willpower, then I might, of course, you know, edit this out of the video, but because I tend to like to do these in one cut, it might be that you get to see quick, behind the scenes of how I set up the camera. So let me just stoop, and maybe I should go a little higher. How is that looking? How is that looking? Okay, I think that's about right. So hello everyone, welcome back. Welcome back. Let me just lock this in place now, and we're gonna get some find some new space. Okay, here we go. All right. Sorry about that. Back to the video, back to the math. Maybe that was a good break, actually, right? It's good to take breaks every once in a while. Right. So, let's think about what is multiplication in n. So, we're going to have a base case, which is multiplication by 1, right? So, we're going to demand that multiplying by 1 always gives you the thing back, right? That's going to ground us, right? So for a specific value, so if 1 appears in the expression, we're going to just arbitrarily decide that that's going to give us, or we're arbitrarily going to decide what that's going to be. And the way that we're going to decide that is maybe I should have these circles. So 3 times 1. Okay. Is this going to be too high? No. 1 times 1. Let's define that as 1. 2 times 1. Let's define that as 2. 3 times 1. Let's define that as 3. 4 times 1. Let's define that as 4. And so on, right? We're going to define multiplication by 1 on the right. And then let's also do the same thing for the left. Honestly, I'm not 100% sure if this is going to be necessary to do it on both sides. But if it turns out that it's redundant, then we can just realize that at the end. So let's have a bit of fun here. So let's define 1 times 1. Well, I mean, we already defined it as 1, but just to make sure, this is going to align nicely, and then we're going to define, let's see, 1 times 2 as 2, 1 times 3 is going to be 3, and any time we have 1 on the left-hand side, we're going to give back the right-hand side, right? So we're going to have all of those definitions in place, right? Okay, so now we can already do a fair amount of multiplication. Of course, this is just something that we've arbitrarily determined ourselves, and there is an obvious issue here because, for example, so what would 2 times 3, what would that equal? Well, since all of these expressions contain a 1, that means this isn't included in the first list, and all of these also include 1, so this is also not going to be included in this list. So basically, we don't know. We haven't defined what this means, unfortunately. But we are going to define, now we're going to define an inductive rule that is going to allow us to work out what this is. And that rule is going to be distributivity. Okay? All right. So, let's see how that's going to work. So, first of all, let's notice that we can write this 3 as 1 plus 1 plus 1, right? Getting back to the basics of addition, right? That's essentially the definition of 3, if you want to think about 3 that way, okay? So now, wouldn't it be nice? Because, intuitively, right, in the real world, if we want this, in the real world, if we take some amount of 3, then maybe we could decompose 3 into its constituent parts, it's sort of one, you could call this the one decomposition of 3, although that's a stupid name, and no one actually calls it that, but I tend to call it that in my personal math dreams sometimes. So if you decompose 3 into ones, a sum of ones like this, then maybe you'd wish that you could just modify these ones all separately, and that would give you the result, right? So that's what we do, right? That's what we do. So we basically allow ourselves to modify this first one by 2, and then add the second one modified by 2, and then add the third one modified by 2, right? We allow this for our operation. And now, this is going to be 2, this is going to be 2, and this is going to be 2. And why is it going to be 2? Well, it's going to be 2 because of this. We already defined what it means to multiply by 1. When you multiply by 1, you just take the other operand. That's it. So this is going to be 2, this is going to be 2, this is going to be 2. 2 plus 2 plus 2, that's going to be 6, right? So, at least in this case, we can compute the value, right? If we allow our operation to have this property. Now we have 2 questions remaining, right? So the first question is, does this allow us to give a value for every possible product that we might conceive of? And the answer is yes, right? So 2 questions. So does every product have some definition? Does every product have some definition? And the answer to that is yes. And we're going to get to why that is. Maybe you can already see why that is, but that is true. The second question that you always want to ask in these sorts of situations is, and actually we're getting to something that's quite deep in math, that you would maybe not even encounter this on your first year of math studies. We're essentially using the analysis synthesis principle here, which is one of my favorite things in math. I'm so glad that I get to share this with you. But yes, the second question is, does every product, or okay, how should I phrase this? So does the product make sense? Does the product make sense? Right? Does the product make sense? And the answer to that is also yes. But let me first talk a little bit about what I mean, what I even mean when I ask that question, right? So for example, let's say that on top of these rules here, I also had a rule that said that 2 times 3 was equal to 5, right? Let's say I had this additional rule here. Well, in that case, this analysis would lead us to conclude that this product is equal to 6, while using this rule would lead us to conclude that it's equal to 5. And clearly, the result, and this is a part of the definition of an operation, because an operation is a function, and a function has to have a single value. We'll get to that later. But that would be just crazy. It can't be that our operation, our multiplication, is simultaneously 5 and 6. That makes no sense. So in that case, even though it's true that for every product, including 2 times 3, there exists some, reasonable definition. There's, we have an argument to say that it's 6, right? And we also have an argument to say that it's 5, right? Because we just came up with this rule. But nonetheless, our product does not make sense. It's not well defined because we need to have precisely one operation for one result for every different operation or every pair of inputs, right? And this is actually a very general pattern in mathematics. So basically, we are first imposing some conditions on our operation, right? And then we find that our operation must behave a certain way. And then at the end, we have to double check that our operation that behaves a certain way actually exists. Like, you can make a valid operation out of that, because that's not always the case. For example, here, our operation would not make sense, right? So this is called analysis synthesis in mathematics, right? So analysis, this is the analysis part. So the analysis part says how must it behave roughly, right? And then the synthesis part is you checking that the thing that you have come up with is actually valid. It exists. You can define your thing, right? Because just because your hypothetical operation, according to your hypothetical rules, behaves a certain way, does that mean that it, strictly speaking, exists, or it won't run into some sort of contradictory statements like we did here or something, right? So that's called analysis synthesis in math. That's a very deep philosophical thing, and maybe I should apologize for bringing you into some deep philosophical waters. But that's what I like about math. For me, it's about philosophy. For me, it's about being crazy, being creative. Okay, anyways. So, let's see. So maybe you can already see. So why does every product have some reasonable definition? Well, if, so let's say we have, I'm not going to bring in variables, don't worry. But let's say we have 11 here. And let's say 11 times 1032. Well, in that case, we can decompose this 1032 into ones, a sum of ones. So that's going to be 11 times, 1 plus plus, oops. Oh, what is this pen doing? 1 plus plus 1. And then this is also going to be defined according to our rule. So, yes, that's valid. Okay. Then we should also ask, is there only one reasonable definition for a result like this? And if you think about it, maybe you might be convinced that, everything's fine, right? Yeah. Okay. Now, I'm not gonna maybe bore you with all the formal details, but that's the idea. And it turns out that there's no problem. This makes sense. Like, this is just gonna be 11 distributed over 1032 of these ones. So it's gonna be 11 times 1 plus 11 times 1 plus 11 times 1. So 11 added to itself 1032 times, right? Now, while we're at it, let's think about why this thing is commutative, right? So maybe we could take the 2 by 3 example, and let me get rid of this because this was just crazy. So here, these 2 times 1s, let's not actually write them as 2s yet, right? Because we have a rule that says that, or maybe we should write them as 2s actually. Yeah, let's write them as 2s. 2 plus 2 plus 2. Because we have another rule here. We have another rule here that says that 1 times 2 is also 2. So we basically how one should interpret this is that whenever you have multiplication that includes 1, well, then it's commutative. So 2 times 1 is the same as 1 times 2 because they both give 2. So in that case, it's commutative. But is it general for any arbitrary product? For 2 times 3, 2 times 3, is it commutative then? Well, we don't know. We don't know yet. But if it includes 1, then it's commutative, okay? But what about in general? Well, we can turn these 2's into 1 times 2. So we're effectively using the fact that if 1 is included in the product, then it commutes. That's what we're doing here. So we're commuting these 2 times 1's, right? Now, here we actually kind of run into a dilemma, right? Actually, no. Well, yes, but yes. So, strictly speaking, we're gonna, so, listen, okay. Here, I don't know how, if you're not, like, super familiar with mathematics, then, I don't know if this is something that you might see immediately, but basically we can factor out a common 2, right? So we can, instead of modifying this 1 on the right by 2 and adding them 3 times, we can have the 1's here and then multiply the whole sum by 2, right? That's also distributivity, right? But let's be clear that what we used here is this right here is okay, this is getting very philosophical. So this right here is called left distributivity, right? So this right here is called left distributivity because we take this 2 in from the left, right? So the big sum is on the right and the 2 is on the left. So this is called left distributivity. Distributivity. Okay. While this right here is called right distributivity. And I'm not going to write distributivity again, but you get the idea. Right distributivity here. Now, this is interesting. So, do we need to assume right distributivity for our operation? Because, like, on one hand, because I'm inclined to say no, but I'm actually not sure here. Right, so my thinking is that because this left distributivity allows us to define the whole operation, right? So left distributivity and these induction base cases, those allow us to define the whole operation. So therefore, at that point, like, the operation either is or is not commutative, and whether or not we add additional assumptions doesn't matter, right? However, the way that I would like to show commutativity is by, on top of left distributivity, I would like to assume right distributivity. So evidently, right distributivity follows from the distributivity of the commutativity of 1. So these set of rules and left distributivity. Evidently, that means we can show, as a result, that this right distributivity holds. Although I don't know how to do it. It might be messy, it might be crazy. This is getting very philosophical, but anyway, I mean, you know, there's no real issue besides mathematical ego. There's no issue with taking left distributivity and right distributivity as our defining assumptions. And by the way, left distributivity together with right distributivity, that's often just called distributivity. So when we speak of distributivity, we often mean that both of these things hold, right? Of course, when we take both, there's more things to check on the synthesis part. So in that case, it actually might be a little non-trivial, whether there's actually no issues with this thing. Yeah, maybe I should have planned out the video in more detail. So this is getting very scary, but maybe that's homework for you guys. Some food for thought. But anyway, if we assume distributivity, right? Both left distributivity and right distributivity, then now what we found here is that this is a 3 and this is a 2. And that means that we turn 2 times 3 into 3 times 4. And it's not hard to see why you can always do this for any product like this. So we essentially showed, assuming distributivity and these rules, that our multiplication always commutes, right? So if 1 commutes, then every product commutes, assuming distributivity. Of course, whether or not such an operation is well defined, that we don't run into some sort of contradiction somewhere, that would be synthesis thinking. You know, you should do that thinking, but I guess I haven't really prepared that thinking, so let's just hope. Let's just hope multiplication exists. But of course it does. Of course it does, right? Ooh. Yeah, okay. But anyway, we have essentially shown commutativity here. And maybe I should emphasize that, of course, real mathematical proofs don't just show one example and then they say, okay, now we're done, right? Like if this was in a math class, we would obviously be using variables and logic and that type of thing. But for me, I think it's more important for me to illustrate the ideas rather than the formal details, because once you understand the details, once you understand the big picture idea, understanding how to turn that into mathematical notation is just a matter of taking the time to learn that sort of notation. But because I know that not everyone is super familiar with that, I don't want to make these videos inaccessible for no reason by introducing variables and stuff like that too early, at least. I mean, we're gonna have to get to those things eventually too, but for right now, I want to try to keep things relatively simple, even though I do keep getting on these philosophical tangents. Sorry about that. But yes, commutativity, hooray! But the real surprising thing for me was actually associativity. So I actually had to think about that for this video. I actually had never thought about why this multiplication is associative. Then I thought about it for, frankly, a couple of days, actually. It wasn't just something I thought about it. I was like, yeah, no, that's really easy. No, it actually took me a bit, which is, again, it's a reminder that math is not super easy. It doesn't have to be easy. It's not fun if it's easy, at least in my opinion. But anyway, let's get to the final final boss of this video, right? So is the multiplication of natural numbers, is it going to be associative? Let's see. Okay. So, here is where we're going to pick up our inductive proof toolkit, right? So this is going to get a little fancy, maybe. So strap yourselves, or brace yourselves. Sorry, brace in, strap yourselves. Strap in and brace yourselves. Getting those mixed up there. Okay. Yes. So again, the rough idea is that because it's associative. So because it's associative. Because one is associative, and this is very like rough talk here. We're being very rough because, what does it mean for one to be associative? I haven't specified that yet. Because associativity is a statement about an operation in three, it takes in 3 inputs, so, But the rough idea is that because one behaves in an associative way, everything behaves in an associative way. So because one is kind of associative, then everything is, right? So it's very similar as with commutativity, where the idea was basically, assuming distributivity, was that because one commutes with everything, then that means that everything commutes with everything. Okay. So let's think about a simple situation here. So let's put 1 in the middle, then modify it from the right by 1, and then from the left by 1. Well, and then let's compare that with modifying 1 from the left first by 1, and then from the right by 1. Now, these are obviously equal because this is going to be 1, because whenever we have a 1, we take the other operand, and then multiplying 1 by 1, that's also going to give 1, so both of these are going to be 1, both of these are going to be equal, right? Okay. Now, what would happen if we increased, let's see, what do I want to do? So what would happen if I increased this 1 into a 2? So let's say I had 2 here and 2 here. Are these going to be equal? Right? Well, here, this thing is going to be equal to 1 plus 1 because, okay, I'm being very inconsistent with my 1s. My 1s look very weird. Let me just keep doing weird 1s, I guess. So 1 plus 1 times 1. So we multiply by 2 on the left and then by 1 on the right. But we have written the 2 as 1 plus 1. Okay, now according to distributivity, we can distribute this 1, right? So we get 1 times 1 plus 1 times 1. And then that's going to be modified on the right by 1. Okay. Okay. Now, by using distributivity again, but this time, this was right distributivity, right? But this time, let's use left distributivity. So this was right distributivity. This is going to be left distributivity. So we're going to have 1 times 1. 1 times 1 plus 1 times 1. Okay. Hold on. No. Maybe let's use right distributivity again, actually. Right? There's some trial and error, right? So we want to use right distributivity here. So we're gonna get 1 times 1. That's gonna be modified on the right by 1. But we don't want to modify it on the right, actually. Yes, we do. Yes, we do. Right? Okay. Here's the real kicker. Let's see. So 1 times 1. I'm sorry for my terrible ones. Times 1. So all of these are 1s, even though they look really weird. Now, we know from before that 1 is associative, in the sense that this is associative and this is associative, right? So let's say that this is associative, so we can modify the 1. We can modify this 1 from the right first, and then from the left. And we can do the same thing here. So let me, I always like to write the middle one first. That helps me keep track. So modify it from the right first and then from the left. Okay? Now, let's think about the right one. I can feel the retention graph going down on this video. So now we have basically moved this one to the left-hand side here. Yes. But you know, maybe to illustrate the power of this, of what we've done, let's say that in the middle we actually had some really random number. Like, let's say we had we had 69 in the middle. Yeah, I'm childish. I don't know how you can tell. Let's have 69 there. So that means that here, when we decompose 2, we multiply that with 69. So 69 here. And then here, when we use right distributivity, which way is the eraser? Is it this? No, it is the red end of it, I think. Okay, so 1 times 69. Let me just rewrite that entirely, I think. So 1 times 69 plus 1 times 69. Right? And then we can distribute this 1 on the right again. And we're gonna get let me rewrite this whole thing. We're gonna get 1 times 69 times 1. So we have a sum here. Let's modify it by the 1, both of these by 1 from the right. And then we're going to have 1 times 69. 1 times 69 modified by the 1. Okay? Now, let's see. So now we know that, well, okay, I guess we didn't show this in the beginning, but it's very clear that no matter what you have in the middle, this if you have 1s on the sides, then doing 1 from the left first and then from the right, or the other way around, that's going to be the same thing, right? So we can easily show that with anything in the middle, these two are associative, in the sense that we can take 69 from the right first and then from the left, right? And then take the same thing here, 69 times 1 times 69 from the left. Great. Amazing. Now, this, now we can use right distributivity again to conclude that, let's have, so 1 plus 1, and we're going to modify both of those from the right by the 69 times 1. 69 times 1, so that's just right distributivity right there. But this is 2 times 69, isn't it? Sorry, what am I saying? It's 2 times 69. Sorry, it's 2 times, it's you modify 69 with 1 first and then by 2, which is what we wanted to prove. So we just showed that for this triplet of numbers, this whole thing is associative. And notice that like we can generalize this argument for the pair 3, 69, 1 as well. Because if we had 3, 69, and 1, then in that case, let's see. In that case, we would basically have an additional one of these terms, right? So here we had, 1 plus 1. We do this thing. Then we distribute the 1. And then we use the fact that with 1, right? And then we would have 2's here, right? Sorry. Yes. Sorry. No. Okay, should we just, for good measure, should we just do the... Okay, I think we have to do the next one as well. Because otherwise, I'm not going to be able to drive the point home. So I'm sorry. We still have to suffer through a little bit. But this time, we already know the way it's going to go. So let's have 3 times 69. So we're modifying 69 from the left by 3. So that's 1 more than this 2 over here. So let's see if that's still going to be associative. And presumably we're going to utilize this previous result here. Okay, so that's what induction proofs are all about. So let's see here. So we're going to write this 3 as 1 plus 1 plus 1, right? Which allows us to write this as 1 times 69 plus 1 times 69. And I'm using distributivity here. And I'm choosing to write these ones in a slightly simpler way because I feel like it's honestly easier to read if I do this. So 1 times 69. And then we're still gonna multiply that by 1, right? I guess, honestly, because we had the way the 1 works, you can maybe get rid of this 1 here and then just no, I don't know. Let's just, yeah. I mean, anyway. I think you need to do this. Do it this way. So, but yeah, eventually after we're done, you would start increasing this one as well. Okay, so here, what did we do here? So here, when we got to that point where we had, this point, and after that, we distributed this 1 from the right. So let's do that again. So we're going to have 1 times 69 times 1 plus 1 times, sorry, what am I doing? Plus 1 times 69, 1 times 69 times 1 plus 1 times 69 times 1, right? Okay. Now, we know, sorry, I'm being very, very verbose here for no reason. This is not going to highlight the inductive structure of this. So instead of having done this, I mean, honestly, like, this also works. I just realized that this works, so we don't even need to have induction here necessarily. But I think it would be cleaner to have induction here, and it maybe highlights the principle better. I don't know, but basically, I'm going to change my strategy up a little bit. So instead of having this big composition, my strategy is going to, listen, that would have worked, right? We could have done the same thing as there, and it would have worked, okay? But alternatively, we can decompose this 3 into 2 parts, right? So that 3 is going to be 2 plus 1 times 69. Now, why is that good? Well, 2 is good because we already know that 2 is, in some sense, it behaves associatively. And 1 is good because 1 is an easy number to work with. We already kind of know that 1 behaves associatively, right? So we're checking whether the next number in this position makes the whole thing behave associatively, right? That's what we're doing. And the other way could have worked too, where we write this 69 like a whole bunch of times. Yeah, that works, but this is maybe nicer. So we have 2 times 69 plus 1 times 69, all of that times 1 here. And then we're going to have 2 times 69, 2 from the left first, and then 1 from the right, plus, this requires some serious patience, I'm sorry. So 1 times 69 times 1 from the right. Okay? Now, this first thing is going to be associative because here we proved that this is associative, right? So this first thing is associative by virtue of what we've already shown. So it's going to be 69 times 1, all of that times 2. Second, and then this thing, well, that's just 1s on the sides. So again, this is going to be associative. Right? Okay. And now we can use right distributivity, yes, to conclude. Are we going too low? Almost, but not quite. I feel like I should maybe go higher because this is getting very risky. Okay? I mean, maybe you already see what's happening here. So let me just draw an arrow here. And we're gonna say that why does that look so weird? There's an equal sign here, right? Here. It's an equal sign. Is that what? My OCD is killing me. Yeah, I guess that just looked ugly because of angle distortions that happen with the VRChat camera because blah, 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 something geometry. Anyways, moving on from that. We get that this is going to be equal to, it's getting harder for even myself to see, all these 2s and 1s, they kind of, this inconsistent font or handwriting where I write the 1 in different ways in different places. Sorry about that. I need to not do that. That's horrendous. But anyways, we get that this by right distributivity is equal to 2 plus 1 times 69 times 1, where we multiply 69 from the right first and then from the left, which is what we wanted to show. So look here, we came full circle. We showed that that multiplying 69 by 1 first and then by 3 is the same thing as this, right? So that's associativity. And this is sort of the reason we would call this an inductive proof is because we decomposed this 3 into the previous part and some new part that we know how to handle, right? So this 2, that's going to be fine because we already computed that 2 works nicely there. And this 1 is going to work because 1 is just a nice number. And you could imagine that if we put a 4 here, everything would also work, right? And you could imagine that we could do the same thing if we added, or if we turned this 1 into a 2, and then that 2 into a 3, and so on. So basically, the number in the middle effectively doesn't even matter. So you can imagine that by doing this, we can basically generate a proof for every triplet of numbers that shows that the multiplication operation is associative, right? And I should have prepared more for this video. Okay, this was a bit of a mess of a video. This is probably like one of the harder videos in the series, maybe, because I got very technical. Well, I tend to do that. Sorry about that. But yes, so what are the big ideas? So, multiplication is associative because we can show that inductively, right? It's associative because 1 behaves associatively, and we define multiplication sort of recursively or inductively by decomposing a number into smaller parts and then modifying those smaller parts individually, while keeping in mind that modifying by 1 always just returns the other operand. And did I already say it's commutative? It's commutative because we sort of define 1 to be commutative with everything. Of course, there you could have like different equivalent ways to think about it, but that's the way I like to think about it. And yeah, we didn't really go through any computational examples of like 8 times 7. What's that? That goes into the field of mental arithmetic. I don't find that terribly interesting. You all learned that in elementary school. Hopefully, of course, if you struggle to compute 8 times 7, then that could be a good thing to practice, but that's very different from the theoretical foundations, which is the stuff that I, as a mathematician, am interested in. But yeah, that's about it. That's about it for today. So thank you all for watching. It was a bit of a longer one, presumably. Let me actually check. Well, maybe, no, it wasn't that bad. I mean, compared to how technically maybe little we went through, maybe it was a lot, but, this is such a fundamental thing. We use multiplication all day, every day in math, so let's get to be aware of the nitty-gritty. But anyway, I hope you enjoyed it, and or at least managed to suffer through it without suffering too much. And yep, I'll see you in the next one. Goodbye. See ya.